Hey guys, welcome to the second recitation. I have a question. Have you seen the video that I posted last night? Did you get it?
Yeah, I got it, but I didn't watch it because you sent it like super late, man, and I got some stuff to do.
Problems here at home, so I have to go to the office sometimes, and I prefer to not to go during the day when there is too many people there. So anyway, so this is what I'm going to do from now on. When I don't have, when I don't cover the entire material for that week, I'm going to do another video so that I don't want to rush through things like put everything together in just 1 hour and 30 minutes. I feel like the lecture number 2 was something like that. I was in a big rush all the time, and I didn't like that. So that's why I did another video where I went at a slower pace. Anyway, let's get started. I think I gave you some problems to solve, right? And those problems, right, if I look at the list, I think there were, I gave you the following problems. If I look at the list, all right, so the first problem was the following. Was this, so problem 9. Which says the following: for positive integers, n, let the numbers Cn be determined by the rules, by the following rules. And you will see that I have a type of recursion here. C of 1 is 1. C of 2n is C of n. That's interesting. And C of 2n plus 1 is -1 to the power n times C of n. And now we're asked to find the value of this sum, the sum from n equals 1 to 2013 of Cn times Cn plus 2. Okay, so this was a Putnam B1 in 2013, right? So that's what this is the problem, right? It's well, I wouldn't say it's the trickiest problem you will ever find in your life, but it requires some kind of well, some observation, I would say. So, did you try this one? So what do you need to see here? Well, let's look at this. We have to explore these two conditions here. You see this one and this one. Maybe we can find some kind of a relationship between these two. You know, the trick is the following. Well, I won't say a trick, but anyway, if you want to call it like this, let's look. We look at, since I have the C2n plus 1 and C2n, let me look at the next one. Let's look at this product. And now C of 2k plus 1 times C of 2k plus 3. Right? Let's look at this guy. And well, according, I will, for this product, I will use the second relation, right? So this would be -1 to the power k times ck right? And the second one, it will be, instead of the 2k plus 1, 2k plus 3 is negative 1 to the power k plus 1, right? Keep in mind times ck plus 1, right? Because keep in mind that this guy here is nothing else than just 2 times k plus 1 plus 1, right? And I can use the second relation to get this, and this will give us the following negative negative 1 to the 2k plus 1, which would be negative 1, so it will be negative ck, c of k, negative c of k plus 1. Wow. So let's write it again so that we can see it. And I'm going to write it with red so that c of 2k plus 1 times c 2k plus 3 is nothing else than just negative c of k c k plus 1. Well. So we have this. But now if I look at my sum, just look at what I have to compute. Look at this guy here. Let's look at it very carefully. And I'm going to do the following to this sum. Now we have that. Let's look at it. The sum from n equals 1 to 2013 of Cn times Cn plus 2. I want you to look very carefully here, because you see I have the relationship that let me denote this by star. The relation, the equality that I obtained earlier, it involves Cn and Cn plus 1, not Cn plus 2. So maybe I should do something about it. And the trick is the following. Let me look at it. Let me write the first term because I have from n equals 1 to 2013. So let me leave that. So this will be C1, right? Times C3 plus the sum from n equals 2, right, to 2013 of C n Cn plus 2, right? And now I should do something about this sum here. Maybe I could do something to relate it to the equality above. And what I'm going to do will be the following. So this would be equal to, I want you to bear with me, C1 times C3. And now I'm just gonna do the following. And I will take n to be some kind of a 2k. So this will be, I can rewrite the sum as, I will change the index from k equals 1 to 1006. And now, all these terms of this form, right, of...
Wait, how'd you get the 1006? How'd you do that?
Wait, just a second, I will rewrite the sum right now, because you will see that I'll have here C2k, right, instead of n, because you reduce it by 2, times C2k plus 2, right, plus C2k plus 1 times C2k plus 3. So this is how I rewrite my sum. Right, I have the odd, so these are the even ones. So I divide this sum into even and odd, and I just sum them in because I already know how they look like. And these are the odd numbers. Right? Imagine that the 2k is n. So it's 2k is n, you'll get exactly, you multiply by 2. So this will give us, right? So that's the trick. But if you look here, this guy here is nothing else than just 0. If you use star, right? Because so this will give us that this is nothing else than just C1 times C3 plus 0. So C1 was 1. Which is C1 times C3. This was 1. And C3 will give us what? If you plug it in, will give us -1. So this is just -1. That's it. That was the trick. Anyway, this was the first problem. Now let's veer towards problem 10. Problem 10 said the following: show that if Hn is 1 plus 1/2 plus 1 over n, so this is the harmonic sequence. Let me just say it here, the harmonic sequence. Then we have the following inequalities. Actually, from this inequalities, it will follow that the harmonic sequence diverges. The first one, then n times n plus 1, everything to the power 1 over n, is less than n plus hn, or all n greater than 1, and n minus 1 times n to the power -1 over n minus 1 is less than n minus hn, for n greater than 2. So this was a harder problem, Putnam B6, 1975. This is a very nice problem. So I want you to look at it. Did you think of this one? This is it's harder, I admit. But it will, but it has some ingredient here. I mean, if you look at it. So what is the first thing that comes to your mind when you look at this problem? When you have the end root of something, or maybe let's just rewrite this a bit. Maybe we can see it better. So rewrite the first inequality as in the following way. Well, let's group the. Okay, let me write it in this way. So 1 plus, okay, n plus hn. This is n plus 1 plus 1/2 plus 1 over n. And I have to show that this is strictly greater than n times n plus 1, and I have the n root here. Does this ring a bell to you when you look at this? Or even better, maybe let's break this n into n ones. So we will have that 1 plus and group 1 plus 1 over 1. Let me put it this way so that you can see it. Plus 1 plus 1/2 plus 1 plus 1 over n is greater strictly than n root of n plus 1. Okay, and this, right, and this the form, does this ring a bell to you? Does it remind you of something that we discussed? I think even last week we discussed about it. It's a very famous inequality that you see that involves the n root, which is called what?
I'm going to put myself out there, and I'm 100% wrong. But the Cauchy, I don't know.
What do I have in on the left hand side? Is okay. First of all, I want to how many. This is n terms here, right? It's a sum, right? Or maybe even better. Or even better. Let me rewrite this in the following way. Look here. 1 plus 1 over 1 plus 1 plus 1/2 plus all the way 1 plus 1 over n. Everything over n, right, is greater than the n root of n plus 1. What do I have on the left hand side? What is that expression on the left hand side? Is the arithmetic mean, right? And on the right hand side, you have the n root of n plus 1. Maybe that would be the geometric mean. So maybe I should apply AMGM. By the AMGM inequality, or maybe I should say it like this. Recall the AMGM inequality. Right? Arithmetic geometric mean inequality. Which said that, what did it say? That alpha 1 plus alpha 2 plus alpha n over everything over n is greater or equal than the n root of alpha of the product. Alpha 1 times alpha 2 times alpha n. Remember that? Well, in our case, guess what? We will apply AMGM inequality with alpha I to be exactly 1 plus 1 over I. And we have, okay, for I, with I starting 1, 2, n, right? And we get the following. What do we have? Well, let's do it. The first term alpha 1 is 1 plus 1 over 1, which is that. So we'll have that 1 plus 1 over 1 plus 1 plus 1/2 plus 1 plus 1 over n. Everything over n, right, is greater or equal than the n root of the product of these alpha, which is 1 plus 1 over 1 times 1 plus 1/2 all the way 1 plus 1 over n. And now let's do the computations here. So this guy, this I have the square root here, this guy is the n root of, and now let's see, this is 1 plus 1, will be 2 times, the second one will be 3/2, 3 over 2 times the 1 plus 1/3 will be 4/3. Wow. Times, and we keep going all the way to, let's see, 1 plus 1/n minus 1. Let's take the last, not the last one. So that would be n/n minus 1 times the last one will be n plus 1/n. Guess what happens? Look, boom. Probably this one will go with this one here, this one with somebody here, this one here. The only guy that's left is n plus 1. Well, that's exactly what we wanted to prove, which is exactly what we wanted to prove. Right? So it's just, basically the only thing you had to do is just to rewrite the inequality and to apply the AM-GM inequality, and that was it. Okay, but do you see here, my problem says that the inequality is strict. The question is, do we have equality? Does the equality case hold true? Case hold true? That is the question. Well, when do we have equality in the AM-GM inequality? When all of them are equal. So in our case, we have equality in the AM-GM inequality if and only if all those alpha i's are equal. And in my case, which means, in our case, this means that these guys, 1 plus 1/1 is the same as 1 plus 1/2, which is the same as 1 plus 1/n, which is impossible. This cannot be equal, right? And that's it. So that was the first part. And guess what? The second part is identical if you look at it, right? It's just, you have to rewrite it. So the second inequality, I'm just going to rewrite it and I'll leave it to you, is almost identical. And guess what? What are we going to do for the second part? So we rewrite the inequality as, man, this sound is annoying. As what? As n minus hn, right? So I rewrite this as n minus 1/1. So this is minus 1/2 minus all the way to minus 1/n. And now let me group this together. So I'm going to do the same thing. I'm going to break this n into n pieces. And what I'm going to do is the following. Well, I have to show that, yes, it will be, let's group them here, 1 minus 1/1 plus 1 minus 1/2 plus all the way 1 minus 1/n. Again, I have here n terms. This is, and again, by the AM-GM inequality, by the AM-GM inequality, we have So at this point, you know how to apply it. It's 1 minus 1 over 1, which is nothing else than 0, but anyway, let's rewrite it. Plus 1 minus 1 half, plus all the way, plus 1 minus 1 over n, everything over n, right? Because I have here n terms, is greater or equal than the nth root of this product here. You see, I have a problem here if I put the product, because I will get 0. You see, that would be not smart of me to do so. So maybe I should do something here. You see, if I put here this guy is already 0, so everything will be 0. So I don't prove anything. So that's not smart for me to do so. So maybe what I should do, I should just get rid of it. Just get rid of it. I mean, it's 0. I don't need it. This guy just vanish. Okay, let me rewrite it again. So instead of, so this guy is 0 here. So just instead of having n terms, I'll have n minus 1. Right? And I'll put here over n minus 1 will be greater or equal than the n minus 1 root, right, of their product. 1 minus 1 half. Let me put another one. Times 1 minus 1 third. And we're going all the way times 1 minus 1 over n. Right? So this will be equal, which is equivalent with. So that was the main thing that we need to see here, that one of the terms was 0, so we can just get rid of it, which is equivalent with the following. With what? With this guy, 1 minus 1 half, which plus 1 minus 1 over n is greater or equal than n minus 1 times the n minus 1 root of this product here, which is basically the same, is 2 over 1 times 3 over 2 times all the way to n minus 1 over n. So at some point, right? And at some point you will get the exact, this is n minus hn, anyway. And I'll leave it to you from here, etc. The details, it's an exercise for you to complete the details. At this point it's quite clear. Anyway, so that was a problem number 10. Now, the other problem that I asked you to think about was the following, problem number 13, which again was an all Putnam problem, which says the following: determine all polynomials P of x such that P of x squared plus 1 is P of x squared plus 1, and P of 0 is 0. This was a Putnam A2 in 1971. Okay, let's look at it. You see, this is a functional equation with polynomials this time, which, well, I didn't quite cover this exact topic. I did something about polynomials, and I did something about the functional equation in the last video. So let me show you what is the trick here. It will involve some kind of a little bit of combinatorics, which we'll cover later on, but this is basic combinatorics such as pigeonhole principle and so on. Anyway, let's look at it. Let's point out some remarks first. Do you have a good candidate for this? What do you think is a good candidate? Can you see one? If you look at it, what is that polynomial that you see that verifies this functional equation? For example, if you look at what? P of x equals x, right? So P of x equals x verifies our equation, our equality, let's say, right? If you replace it here, you'll have x squared plus 1. First of all, P of 0 is 0, that's obvious. And P of x squared plus 1 is x squared plus 1. And P of x squared plus 1 is x squared plus 1. Well, that's a good candidate for us. P of x equals x. The question is this the only one? Well, let's look at it. Let's do some observations. So as you can see, this is a polynomial. It will have degree n, right, let's say. And now what we're going to do, let's notice some things. So we know that P of 0 is 0. Now let's look at P of 1. So what do you think of P of 1? Let's, for x equals 0, we have what? P of 0 squared plus 1 is P of 0 squared plus 1. Well, this is equivalent with what? With P of 1 equals P of 0 squared plus 1. But P of 0 is 0, so this guy will give us 1. All right, so I know that P of 1 is 1 at this point. That's great. So P of 1 is 1. This is 1 here, not 7. P of 1 is 1. So I have this information about P of 1. Now, let's look at something else. Maybe I should look at P of 2. So what about P of 2? Well, let's look at it. This can be obtained for x equals 1. Since this holds for all x, I can plug in any values. For x equals 1, we have what? We have that P of 1 squared plus 1 is the same as 1 squared plus 1. Oh, sorry, what am I doing here? Is P of 1 squared, P of 1 squared plus 1. Okay, so this guy, which is equivalent with what? With this guy on the left-hand side is P of 2, and this guy on the right-hand side, this is, okay, P of 1 squared plus 1, but this guy is 1. So again, this will be 2. So we also have P of 2 equals 2. So we have, for 3 values, P of x is the same as x. And now let's generalize this. So I have a hunch that P of x will be x. And let's generalize these observations. So that's what we're trying to do. All right. And now I'm going to explain that in the following way. Well, it says that when some number n, let's say, satisfies P of n equals n, well, one can generate another one, another number, let's say another number larger, which is larger. Okay, let me call this number m, let's say, m, which is larger. Right? Such that P of this larger number, P of m equals m, right? It's quite clear. And let me be more specific here. How do we generate this larger number? By just taking m equals n squared plus 1. So it's obvious. N squared plus 1 is greater than n. So again, we can generate another one. Well, in this case, this means that that P of n squared plus 1, we know that this is P of n squared, everything squared, plus 1, but this is n squared plus 1. So as you can see, for numbers of this form, n squared plus 1, P of x is the x, right? Okay. So what does this mean? This means that, let's explain everything here. This means that since the polynomial P of x has P of 0 is 0, P of 1 is 1, P of 2 is 2, right? And we keep going. P of m is m. And this holds true for infinitely many m's, right? Because you can take n squared plus 1, and you keep going. So there are infinitely many m's for which P of m is m, or P of n is n, or for example, whatever you want to say. So equivalently, let's I could say that how should I phrase it? Equivalently, m is a root of the polynomial P of x minus x, right? Okay, and now let's see. So by the fundamental theorem of algebra, if I have a polynomial of degree n, it cannot have more than n roots. It has at most n roots. By the fundamental theorem of algebra, that's one of the most essential things in mathematics. A polynomial can only have as many roots as, and then let me emphasize this, as many roots as its degree. That's important. So this implies that since we have that, since p of x minus x has infinitely many roots, as we have seen, by the pigeonhole principle, it follows that it must be the zero polynomial, that p of x minus x is 0. So p of x equals x. That's it. That was the problem, right? So the moral of the problem is the following. If you have a polynomial, if you have, let's say, even n plus 1, so if the polynomial is null for n plus 1 values, then it's the null polynomial, because the degree is at most n. So the only escape here is the null polynomial. That's the pigeonhole principle. But here is have infinitely many roots, so therefore it follows immediately that p of x minus x is 0. Well, it was a little bit tricky, but anyway, if you know this, it follows quite. It's pretty straightforward. All right, since I'm in a big hurry and I want to do another problem, that was problem 14. And let me do this quickly. Problem 14, if I look here, it says the following. For k equals, for k1 to n, let zk be xk plus iyk, where xk and yk are real. Well, we have a bunch of complex numbers here. And of course, I is the square root of -1, the imaginary number. And now we denote by r, let r be the absolute value of the real part of this number plus minus z1 squared plus z2 squared plus zn squared. Prove that r is less than the absolute value of x1 plus the absolute value of x2 plus, wait, where okay, plus the absolute value of xn. Okay, so that was a Putnam B6 1979. So I want you to look at it. And in fact, it looks more scary than actually it is. But let me translate this for you. So translation. What we have to prove is the following. In fact, we have to show that so let's do a translation of this statement, which looks a little bit more ambiguous than it is. The following. So if these z, k are complex numbers, then we want to show that the real part of this number, the absolute value, let's say, of this number, z1 squared, oh my, plus z2 squared plus Zn squared, right? So the real part of it, of this, and let me put it this way, it's everything, okay. You know what, let me write it in this way. So this guy, the 1/2, right? The real part of this guy, okay, is less or equal than, guess what? The absolute value of the real part of Z1 plus the absolute value of the real part of Zn. So that's the translation, right? A complex number has a real part and an imaginary part, right? We can also write as re of Z plus the im of Z, right? Always. So that's what we have to prove. And now let's look at this guy. So let Zk be xk plus I times yk. This is actually pretty straightforward if you look at it. And clearly, if I want to look at this guy, and we have, let's look at this sum here, Z1 squared plus Z2 squared plus Zn squared, everything to the 1/2, right? This is, and let, okay, maybe I should say, and let this guy be not this number, a plus b I, right? And now let's square this. And we have the following. We have that, what? This guy, a plus bi squared, will give you a squared plus 2ab I. And this guy is z squared, okay. So this will give us what? Let's see. So z1 squared. So this will give us, okay, this will give us so z1 squared, this is a squared, okay. So we will have that a squared minus b squared will be, in fact, let me write it in this way. The sum of xi squared minus the sum of ai squared is a squared, a minus square minus b squared. Okay. This is what we're going to have. Where, let me point out where this guy, where well, I missed something here. Let me see. Okay, no. We identified, oh, and, no. Okay, that's good. And we also have, when we identify the real part and imaginary part, and also we have that AB, because when we square this, we have a squared plus 2abi, right? And also here we have the same thing, and AB will be the sum of xi, yi. Okay, that's what we have. So we have these two equalities. Let's look at them. Right, this just come from squaring this relation here. All right. And now there is one thing that we learned, and I think Abby was saying something about it. Let me recall the Cauchy-Schwarz inequality. Which says the following. Which says that, let me put it this way, since we're the absolute value of xi, yi is less or equal than this guy, xi squared to 1/2 times this guy to 1/2. So this is Cauchy-Schwarz. And now let's rewrite this. Let me denote this by, this is 1, let's say, and this is 2, because I want to. All right, so we have this. Now let's see. So from 1, let's combine this with 1. And let's call this CS. Combining CS with 1. We have the following. Let's see, what do we have? Let's combine these two. So we have what? Well, actually not with the 1, with 2, sorry. We have what? We have that AB, we have that the absolute value of AB is less or equal than this, xi squared times iy squared. Right. So we have this. And now we have a discussion. Now, and I'll leave it to you as an exercise because I went over time. So if the absolute value of A, let's say, is greater than this, then you will get a contradiction. And I'll leave the details to you. Right, it will contradict. So therefore, so the absolute value of A is equal than the sum of this. And finish off the problem. And you can finish off the problem from here. And I'll leave these details for you. I mean, there's some, leave this to get a as an exercise for you. Anyway, and this will follow immediately from another Cauchy-Schwarz. So, but anyway, I'll leave the details to you. Okay, I'm going to stop here. I went way over time. Thank you very much.